Assalamualaikum and hi everyone, I'm NAJIHAH Binti HAMZAINI and I will be presenting my final year project which I entitled Metallic Oxides Nanoparticle Solution which alters T1 and T2 relaxation of Agarose gel phantoms. So for the past years, many types of materials were studied to develop an ideal MRI phantom such as Agarose gel. The need of MRI phantoms is to aid in QA and QC process and also to improve the accuracy and reproducibility of MRI absolute signal intensities. There are a few important criteria of MRI phantoms which are human tissue mimicking, stable and easily operated. For our study, we evaluate the relaxivity and uniformity of SNR for all 22 phantoms with different volume mixture of HCl with relaxation modifiers in nanoparticles form and Agarose gel. There were three objectives for this study, which are to compare T1 and T2 relaxation of distilled water and pure Agarose gel phantoms, to compare the effects of gadolinium oxide and iron oxide solutions on SNR relaxivity and on SNR uniformity. Now we proceed with the material and methodology. For phantom preparation, we prepared a total of 22 Agarose gel phantoms and 2 distilled water for the study. Then we stored them inside a desiccator sealed with seal tape and grease. This table summarizes the desired proportion of HCl and relaxation modifiers for all phantoms. Next, for data acquisition, we use Siemens Magnetum Vario 3 Tesla MRI by using a turbo-spin echo for the pulse sequence. For data analysis, we use three softwares: ImageJ for ROI plotting, MATLAB for T1 and T2 curves plotting, and also for acquire data like SNR naught, R squared, and T1 and T2 relaxation times. And the third software is SPSS to check the SNR uniformity by using a K-related sample t-test. Next, we move on to the results. First, we record the T1 and T2 relaxation of distilled water and pure agarose. For distilled water, the T1 relaxation shows an exponentially increasing trend for all ROIs, while the T2 relaxation cannot be determined due to the constant value of SNR for all TE values. For pure agarose, the T1 relaxation shows an exponentially increasing trend, while T2 relaxation shows an exponentially decreasing trend for all ROIs. Next, we observe the effects of gadolinium oxide and iron oxide solutions on SNR relaxivity. For T1 plot, phantoms with gadolinium oxide solution shows a decreasing SNR, while for phantoms with iron oxide solutions, the SNR shows a decreasing trend for a small volume of iron oxide solution and start to increase with TR when higher volume is added. As you can see in this both graph, the relaxation part of the plot is absent in the range of TR used in the study. We believe that the Agarose gel phantoms added with relaxation modifier relax much faster, and their relaxation part can only be observed at TRs lower than 400 milliseconds. Then for T2 plot, phantoms with gadolinium oxide and iron oxide solution both shows a decreasing SNR with increasing TE. Lastly, we also observe the effects of relaxation modifiers on SNR uniformity. The T1 curves for phantoms both with gadolinium oxide and iron oxide solution shows no significant difference between all ROIs, while T2 curves phantoms with gadolinium oxide solution shows a slight difference between all ROIs, however the difference is small. Lastly, phantoms with iron oxide solution shows no significant difference between all ROIs. In conclusion, the relaxation modifiers used in the study have a potential use as MRI phantoms, as it demonstrates a good SNR uniformity between all ROIs and the relaxivity reduced for the T2 relaxation, although the T1 relaxation could not be visualized in both types of phantoms as the signal is already saturated. It is worth noting that the relaxation modifier added to the Agarose gel phantom has a huge on T1 relaxation as compared to the T2 relaxation. Thank you, that's all from me.